Good day to you, wonderful grade 8s, and welcome to the grade 8 Natural Sciences lesson that's been brought to you by WorksheetCloud. If you have a question during the lesson, send an email with your question to grade8@worksheetcloud.com. My name is Mrs. Ernston, and I am the WorksheetCloud grade 8 Natural Sciences teacher. I believe it's really important that you engage and are interactive in this lesson as much as possible, and that is why I'm encouraging you to gather your notes and get something to write with so that you're able to keep a record of this lesson. Where the note-taking is also going to help you is when you come to study for tests and exams, at least you have a written copy or a summary that will cover what we've done in the lesson, and it will assist you in answering any questions and worksheets that you find in our WorksheetCloud activities that we've posted for you. So this lesson, we're going to be covering expansion and contraction. We're going to revise the relationship between heat energy, movement of particles, and the volume of a substance. And we're going to use the particle model of matter to explain expansion and contraction, particularly of solids today. So our future lessons will cover liquids and gases. So I have a problem that I would like us to try and solve in today's lesson. A man builds a house with large windows set in beautiful frames made of brass. The house is in a region where it gets very hot during the summer. Imagine that the owner of the house has a problem. The windows of the house look beautiful in their shiny brass frames, but they keep falling out during the summer months. As a scientist, how would you explain this, and what would your advice to the owner of the house be? Should the frames be replaced? If so, with which material? And what other solutions can you suggest? So I encourage you to pause the video, copy down this problem and the questions, so as we progress through the lesson, you're able to revert back to the problem and see if you are able to come up with the answers. The following diagram shows a metal ball and ring apparatus, and in a few moments I will show you a clip of how this experiment works. The ring and the ball are both made of brass, and at room temperature the ball is just the right size to pass through the ring. So in this diagram over here you can see that the ball is able to pass through the hole in the middle of this ring. So this ball is able to pass through. However, do you think the ball will still fit through the ring when the ball has been heated? Let's go and find out.
So you need a heat source. In this case, I'm simply using a candle, but a Bunsen burner does work best. And whenever you deal with open flame and heat, always have water or something around in case something goes wrong and it needs to be cooled down quickly. First, start by showing the students how easily the ball does fit through the ring. You could even pass this around and have the kids demonstrate it themselves. Next, you would light this candle or Bunsen burner, and then hold this over the flame for about a minute or so until it gets nice and hot and it does expand. Okay, I've been heating this for about a minute now, so when I try to insert this into the brass ring, it does not want to go in there anymore. So then you could have the students heat the ring up so this expands and then it will fit again, or just allow this to cool and show them how it fits in there. One thing you do not want to do not insert these together and heat them both up at the same time. You will get them stuck and it will not come out. This is already cooled down enough that it can fit in there. You may have heard the phrase,
The ball does not fit through the ring when the ball has been heated. Do you think the brass ball will have more mass when it has expanded? See if you can explain your answer. So no, the brass ball cannot have a greater mass because it hasn't gained any mass. So then I wonder why, when we heat it, it can't fit through the ring. So what will happen to the brass ball when its temperature drops back to room temperature? Will it be larger than, smaller than, or the same size as before it was heated? And are you able to explain your answer? So if we think back to the video, when it was heated, the ball couldn't get through the ring. And then after a few minutes, after it cooled down, the ball was able to get through the ring. So does that mean the ball changed size, changed mass? So the ball will contract to the same size as before because it has not lost or gained any mass. So it's just contracted. So that means when we heat the ball up, it expanded, and when we cool the ball down, it contracts. So here we have some diagrams that will help us with the explanations. When solids are heated, the particles vibrate more rapidly, pushing each other apart slightly, causing the solid to expand. So as we go from this picture to this picture, the particles have started to vibrate, and you can see that if we look at these particles here, or these particles here, and these particles there, they have started to move slightly apart. So when the movement of particles speeds up, there is an increase in the space between them. So look at the space between the particles here, and after heating, look at the space between the particles. So that means there is an increase in the space between the particles, which means the substance expands. So here we can see the volume that the substance takes up at a low temperature, and here we can see the volume of a substance that it takes up at a higher temperature. So that means, in other words, there is an increase in the volume of space it occupies. The amount of increase in volume does depend on the type of solid. So what happens if we have a decreased temperature? This is going to cause the solids to contract, and again by varying degrees. So materials can also shrink slightly when they are cooled, and we say they contract. So when the movement of particles slows down, so here we've got a substance and now we are cooling the substance, there is a decrease in the space between them. So look at the difference between the particles here, and look, the distance has become less. So there is a decrease in the space between the particles. This means the substance contracts. So in other words, there is a decrease in the volume. So this is how much the solid took up, and then upon cooling, this is how much volume the substance occupied. In our previous lesson, I left you with an activity of doing a graph where I asked you to compare the expansion of different solids, and I asked you to construct a bar graph where you must put expansion on the y-axis and materials on the x-axis, and we went through graphing skills. So I would just like to recap again on that activity for those individuals that have joined us today. So here is a table, and I've given you different materials: brass, iron, steel, platinum, alloy, concrete, ordinary glass, and oven-proof glass. And then I've given you some data, and this data is how far a 100-meter length of the material will expand when we increase the temperature by 10 degrees. Then I reminded you of the skills you need to remember when constructing a graph. So you always need to remember that your graph needs to have a heading, and that heading needs to tell you what type of graph it is. It needs to mention the dependent variable and the independent variable. On your y-axis or the vertical axis, you must mention the title in units. On your horizontal and x-axis, that also needs a title and units. You must put a scale on the y-axis or on the vertical axis. You must have a scale on the horizontal axis. Now, I know with the bar graph, it's as difficult to do the scale, but I'll explain it just now to you. Ensure that you've done the correct type of graph, which you were instructed to do a bar graph. Ensure that the plotting of your points is correct and as accurate as possible, and ensure that your diagram is neat. So those of you that need a few moments, please pause the video now while you construct the graph, and I'm going to follow up now with the memo. So hopefully this is what your graph looks like, and I will just go through and remind you of each of the skills you needed to remember. This is not necessarily the marks that your teacher or examiner is going to award. I'm more just putting ticks where we need to remember the skills. So you have given your graph a heading and you've underlined the heading. In the heading, you've mentioned that it is a bar graph and that you've mentioned the independent variable, that's the different types of material, and you have mentioned the dependent variable, and that is the expansion in millimeters. Then the fact that it is a bar graph, and then please remember with a bar graph, when we look at the horizontal axis, the space in between each bar needs to be exactly the same, and the width of each bar needs to be exactly the same, and you need to ensure that your bar graph fits nice and neatly on the page. Then when you have a look at your vertical axis, always start your axis at 0, and then always make sure that you follow a linear scale. In this instance, we've gone up in 2s, 0, 2, 4, 6, 8. You can choose your axis so long it is as it follows some type of scale. Then in terms of your horizontal axis, in this case, remember the spacings between the bars need to be the same. The width of the bars need to be the same, and you do need to have a list of the substances underneath each bar. As in, here we've got brass, iron, steel, platinum alloy, concrete, ordinary glass, and oven-proof glass. Then each axis needs to have a title and units. And then please ensure that the plotting of your points is correct, and ensure that your graph is nice and neat. So, for example, increasing the temperature of 1 meter section of oven-proof glass by 10 degrees will cause it to expand by 3,5 millimeters. So if we look at these substances, which substances are all the same? So we can have a look at steel and concrete and ordinary glass are all the same, and we can read off the graph that that is 11 millimeters. Then which substance increases the most? Well, that would be brass, and that is 90 millimeters. So just to get you thinking for a moment, what solid would be the best material to reinforce concrete? So if I was building some type of construction and I needed to strengthen or add something to the concrete, what would be the best substance? Now the hint you need to think about here is the reinforcing material should expand as much as the concrete. Otherwise, it's going to damage the concrete when there is a change in temperature and when there is expansion. So the one thing that you could add to reinforce the concrete is steel, because they both have exactly the same expansion. So how can we use this information to help the man who built a house with his beautiful brass frames? So as a scientist, how would you explain this, and what would your advice to the owner of the house be? So can you use the data that you've plotted here to help solve his problem? So should the frames be replaced? And if so, with which material? And what other solutions can you suggest? So if we have a look at it, he is using ordinary glass that has an expansion of 11 millimeters. So you need to pick a substance that is the same as that. So when this glass expands and contracts with the change in temperature, it's not going to fall out. So according to this graph, you can either make concrete frames or you could possibly use steel. I wonder if you have any other solutions. So from the graph and the data in the table, we can see that brass expands much more than ordinary glass. Here is brass and here is ordinary glass. Look at the difference. So when the weather is really hot, the brass expands so much that the window glass doesn't fit properly anymore and is going to fall out. So what could you advise the owner to try? He could replace the brass frames with steel. The steel expands by the same amount as glass, and the glass should stay in place. The other solution, and I wonder how many of you thought of this, was could he possibly replace the large windows with smaller windows? Because smaller items expand less because there is less matter that can expand. Just a note, in addition to the type of material, the amount of expansion also depends on how much material there is. And that is why expansion is sometimes difficult to see, particularly when we're looking at relatively small items. So a key fitting into a lock or a pot on a stove. So sometimes the key will still fit in the lock even though it's been lying in the hot sun. And sometimes the aluminium lid or the glass lid will still fit on the pot even though the pot has been bubbling and boiling on the stove. So the expansion is not always necessarily noticeable in these small everyday items. But when we are dealing with larger items like the construction of roads or buildings or houses or bridges, this difference in expansion and contraction could have a significant impact. One thing you can think about is that power lines need to be hung from poles at the correct tension or tightness. If the tension is too tight, the power lines will contract and break in cold weather. And if the tension is too loose, they will expand and hang too close to the ground in hot weather. Even though the amount of expansion and contraction in solids may seem quite small, it can have serious implications in certain situations, such as the construction industry. So here you can see the cement and the steel that has been used to create this bridge, or what about the materials that we use when we create tar roads? Very important principles to remember when building bridges. So when engineers design a bridge, they must allow for contraction and expansion of the materials used to build the bridge. Have a look at the following photo showing a close-up of the gap between two road surfaces of a bridge. Can you see interlocking teeth? These allow the bridge to expand and contract while the teeth slide past each other. Now, isn't that really, really clever? So just to recap, there is a relationship between particle movement and volume. The density of solids will remain more or less constant no matter what container they are placed in. And this is because their particles are relatively close together and they have strong forces between them. But what happens when a solid is heated or cooled? This is the same as giving them extra or more or less energy. So you should now be able to answer the question, how will heating or cooling solids affect the packing of particles and the density? So we have seen that changes in heat energy affect the movement of particles even if there is no change in state. And an increase in heat energy makes the particles move faster, and changes in the rate of particle movement result in changes in the volume occupied by that substance. And we've seen that changes in heat energy affect the movement of particles even if there is no change in state. And what happens if we have a decrease in heat energy? It makes the particles move slower and the particles move closer together. And this is why most materials contract when they are cooled. So the changes in the rate of particle movement result in changes in the volume occupied by that substance. So to make your thinking visible for this lesson, you can design a thinking diagram like this, where you can put the contraction and expansion of solids in the middle. You can have a column where you provide all the definitions for contraction and expansion. What examples can you give from this lesson? What characteristics do we associate with a contraction and expansion in particularly solids? And are there any symbols or any colors that you would like to associate with contraction and expansion in solids? And if you make a nice visible thinking diagram like this, that means you've got a nice summary for when you write tests or exams. So what have you learned today? You can write down 3 things you discovered, 2 interesting facts or details you can remember, and 1 question that you still have. And if you are unable to answer this question and it's affecting your ability to understand the work, please can you email your question to grade8@worksheetcloud.com. Thank you for watching Grade 8. I so enjoyed having you in my lesson today, and I would like to thank WorksheetCloud for bringing you this lesson. Goodbye, Grade 8s.